Hello, my name is Clint Guyman. I've worked with Joseph Tuft, who's a sophomore in the BYU Chemical Engineering department, and we presented on climate change and kinetics in a terrarium at the American Society of Engineering Education recently. And I wanted to share that presentation with you. So, CO2, we all know, has been released from underground sources for a long time, whether it's from oil or coal, to provide our energy needs and transportation needs. That CO2 or carbon source was converted to CO2, and that CO2 concentration is increasing. That's well documented, as well as the rising temperatures in our atmosphere, and surface temperatures as well as ocean temperatures. So as part of our chemical engineering laboratory activities, we thought it would be great to use a terrarium to kind of draw attention to some of those issues and gain some insights, while also being effective in using the principles of chemical engineering, such as kinetics and diffusion, to analyze a terrarium space. And we understand it's a crude way to estimate the atmosphere, but it is one way. A terrarium is great. This one is about 7 gallons, and so think of about a basketball size width, and it's a little taller than that. And you have your foliage, of course, your plants. In this case, we stuffed them through this little hole at the top, you'll see here in just a minute. And it has some soil, of course, and under the soil, or you can disperse it, but here it's a little concentrated area of activated charcoal to help with some of the toxins that can be present and absorbing other unwanted items. And then, of course, you have your rocks there at the bottom to help with water management. There's a water cycle, an oxygen cycle, and a CO2 cycle, carbon cycle in a terrarium. In this laboratory activity that's just one lab long, just an hour, we inject CO2 into the terrarium, the sealed terrarium space, and we measure the concentration before and after to determine the internal gas volume in the terrarium. It's a nice little mass balance that can be helpful to gain experience doing mass balance problems. And then the second part's the kinetic-based piece, where students measure the rate of uptake of CO2 by the plants. So the two different exercises, one of which is with a closed terrarium, it's capped. The other one is when it's open, and when it's open you can have diffusion of the higher concentration of CO2 from inside the terrarium out the top. So you have a mass transfer scenario there. And the kinetics of CO2 uptake by the plant depends on the CO2 concentration inside the terrarium, as well as the intensity of light. As far as that rate, it varies. And then you can use all of those pieces and get a transient mass balance to get the concentration as a function of time of CO2 inside the terrarium. The sensor used to measure CO2 is a SCD30 is its device name, and I think you can see my pointer here, but that's what it looks like right there. And then we couple that with an ESP32, and there's firmware or software that Sensorion makes available. It's pretty easy to upload onto your ESP32 microcontroller, and then you can access the data real easily with an app that they provide, and it makes it convenient to plot on your phone, whether it's an Apple or an Android, and that works seamlessly for greater than around 80 students. And you can also export the data. So the hardware that we also used for injecting the CO2 into the sealed terrarium is shown here. We filled this tube sections like 2.5 cc's volume between the two valves with 10 psi of CO2, and then you can connect it to this downspout that goes into the terrarium and seals it off, and it's valved as well with a little needle valve right here, and then you can push the residual CO2 through the tubes with this syringe, and then here's the size scale of, that's the SCD-30 that was shown in the previous slide. And here's a little video showing its use. Let's see if I can get it to work. Is it going to play? It's not going to play. But here's where you connect that tube section up to the manifold or the gas regulator on the CO2 bottle. And then you can connect it here. It shows the downspout into the terrarium. And you can open the valves, allow the CO2 to enter into the terrarium that's sealed, and then you can use the syringe to push any residual CO2 through there. Oh, it's playing right there. It'll take just a minute to go through that first step. First purge it with some CO2, pressurize it, and close that upper valve, close the valve and remove it, and then the other one is connecting it up to that downspout portion, and then opening the valves to dose it with the CO2. Syringe. Yeah, here's example data showing the different concentrations. So the blue line is the data, and you can see it starts around 4,500 parts per million of CO2, and then on the bottom axis is time in hours. So the time frame for this was a couple of days. As it decreases, this section, 8-hour section for instance, is at a given light level, and then like the room lights, and then those are shut off, and the CO2 rises, and then you like a lamp was put on the terrarium, and that CO2 level decreases substantially, and then is shut off, and it rises again. There's quite a bit. Why does it rise? You're like, why is the plant making CO2? No, it's the bacteria that is breaking down the carbon. That's producing a significant amount of CO2 inside the terrarium. And the humidity and temperature stays relatively constant. So we're quantifying the uptake of CO2 as a function of time, as well as the gas concentrations, and those can be correlated to our atmosphere. We know that burning of fossil fuels emits CO2 into our atmosphere. And similarly, in our terrarium, we injected some CO2 into the atmosphere. And so integrating that over time can give us a function of an estimate of our CO2 concentration. And here's our classic mass balance for the CO2 inside the terrarium. Our accumulation term equals our in minus out minus our consumption and generation added to our generation terms. So we have some generation by our bacteria, and that generates CO2. There's some loss of CO2 out the top of in this case it's the open terrarium, and then there's plant consumption of CO2 there. And so you can, this term is given to the students as far as the generation by the bacteria. They're also given this diffusion coefficient, and this is the 400 ppm that's out in the room approximately. And here's our kinetic rate constant for uptake of CO2 by the plant. Here's our light level right there. And with that, you can integrate this equation and get an estimate, and that's what that plot was. It's not letting me go back, but the model, you can get a model of what the actual CO2 concentration is doing, and then use that model to predict what would happen for other scenarios. So the students, 80 students participated in this lab approximately. Here's some student outcomes that they were queried about in terms of if the laboratory activity increased their awareness and complexities of the Earth's atmosphere. The majority agreed. They were asked if it increased the awareness of some of the sources of carbon dioxide, as well as if it increased the awareness of plant life and photosynthesis processes. And the majority did agree that it did. Some responses: I enjoyed this lab. I thought it was cool. Look into the Earth's atmosphere and how plants control CO2 concentrations. And it was interesting to see a small scale example of how the Earth and atmosphere work on a larger scale. Some other ones, evidence of how CO2 can impact the environment, including bacteria and plants. This lab changed our thinking about the atmosphere because we thought of it as a big ball of gas rather than a transient mole balance with lots of different reactions going on. Some alternate activities. This is another terrarium. This one Joe built. You can, instead of observing the CO2 concentration, you can use the sensor and light as a control laboratory. So you could control the CO2 concentration with the amount of light that you've got. And here's an example setup where you're measuring the reading in from the Terrarium SCD30 and ESP32 microcontroller, the CO2 concentration, and then using that concentration to vary the light. So if it's a higher concentration of CO2, you'd increase the light, and vice versa. And then you can control the CO2 concentration, and that could be using PID control or other control strategies. You could do that as a laboratory activity. So yeah, and in conclusion, the Terrarium lab activity we had success with this last semester, and students were able to quantify some of the diffusion rates and kinetic uptake of the plant of CO2. It was an engaging laboratory, and it fostered discussion and reflection on our current environment. That's it. Best wishes.